Hello, this is Dr. Marina Sabrajmail from the Lebanese University. In this series of 6 chapters, we are going to cover an overview of PLCs or programmable logic controllers. We are going to go over the hardware and basic software programming for the PLCs. In this chapter, we are going to see the origins of the PLC, security measures that have to be taken when using a PLC. We are going to talk about their advantages and their block diagram with the different parts within, and we are going to talk about the IEC code that organizes their programming. A programmable logic controller, in French we call it an automate programmable, is the name given to a type of computer commonly used in commercial and industrial control applications. These PLCs store exactly one program in their memory. They contain modules to read inputs and control outputs. Originally, these PLCs were developed to replace relays in the late 1960s. Their cost then dropped, so they became popular by the 80s. They are now used in many industries for the several advantages that they have and that we will discuss. When we talk about a PLC, we are talking about a controller that is controlling automation and in industry. So we have personnel that are next to the machines, and if the machine control fails, these personnel have their life at risk. This is why when we are programming a PLC, you have to take care that the machine itself has to have several emergency stop buttons, double safety sensors in case just anyone fails to work, the machine doesn't get off of the rails and hurt somebody or break itself. We have to put a lot of lamps and alarms in case the machine is working, and in case the machine has times where it has waiting times, so the machine is not moving but it's still functioning. Advantages of PLCs are several. One of them is to eliminate much of the hard wiring that was used when we were controlling with relay circuits. So the control used to be made in a large number of relays, and this has been replaced by the ladder program, and the ladder program is just a software where we draw the different relays and their contacts, and we replace actual physical relays in the control. They have increased reliability because once a program has been written, it can be downloaded to many different PLCs, so we can have a copy-paste just like any softwares, whereas when we used to work with relays, this has to be remade all over again. Plus, when I am wiring a relay, I have a lot of problems when a wire doesn't fit correctly, and here we have a much reduced problem of wiring because the wiring has been reduced to only the inputs and the outputs of the PLC. We have more flexibility because it is easier to create and change a program in a PLC than to write and rewrite a circuit. So anytime I want to modify anything, I just can go back to the software, change it. Plus we can have a lot of simulators so to verify before actually putting it onto the machine. You can have software simulators as well as hardware small circuits. It has a lower cost, so the cost of the PLC is less than the cost of a lot of relays. We have in here a general thumb rule. If an application requires more than 6 control relays, it will usually be less expensive to install a PLC than to control by relays. Less than 6, go ahead and work without a PLC. It has communication capabilities. A PLC has the capability of communicating with other PLCs or other computers or a server, and therefore we can put within a system, could be a SCADA system, so that we can network and can see the control of each machine and each PLC from one centralized computer, for example. It has a faster response time. PLC operate in real time, which means that an event taking place in the field will result in an operation or output taking place. So it can deal with boxes or items that are going at thousands of items per minute, for example. it is of course easier to troubleshoot than when you look at a table of plenty of relays and plenty of wires, because you have the software in front of you. You can look at the values of the inputs and the outputs, so it's much easier than older circuits to troubleshoot, find the errors. The block diagram of the PLC. In a PLC we have a central processing unit, a memory which is divided into a program memory and a data memory. You have input modules, output modules, power supply, and the programming device. We're going to discuss each of these parts alone. So before we talk about the different parts, we have two types of PLCs. We have the PLCs that come as one module, one unit, and you have those that come with a PLC rack. A PLC rack is a rack, a hard block that can hold the different parts of the PLC together, which is the CPU, the input module, the output module, and the power source all together. Whereas when PLC comes in just one block, everything is inside. So the power supply of the PLC supplies the DC power to the other different modules that plug into the rack. The power supply also supplies the power to the CPU, and it changes the input power to power required by each one of these units. So for example, in here, if we have a 115 volts AC power supply input power to the PLC, this cannot be the power that the inputs and outputs are going to use. They could be 20 volts, 24 volts, and we can have the 5 volts for the CPU, for example, and this power supply is going to change the 115 volts to 5 volts DC for the CPU and whatever the inputs and outputs require. So the user also must determine how much current will be drawn from the input-output modules to ensure that the power supply will supply enough current for all of them. If not, we have to reduce the power that is outputted from the output modules by adding external relays. The processor, or the CPU, this is the brain of the PLC. It consists of a microprocessor for implementing the logic. It is designed so the circuit can be entered in relay ladder logic form. So within the basic program, it is adapted to ladder logic as well as other different programming ways. But the most common in PLCs is the ladder logic. So the processor is the unit that was going to take the information from the sensors, execute the stored program, and send the appropriate values to the outputs. CPU has different modes. So we have programming mode, we have the run mode, and we have the remote mode. In the programming mode, it is where we are going to write and download the program to the PLC. So it is a mode where the PLC forces all the outputs into off, because if I am downloading a program and I get just any value intermediate when I am downloading and the machine is on and the outputs are on, I can be controlling the machine in the wrong way. This is why program mode is very important, and the PLC does not allow downloading a program out of it. The run mode is when the PLC is running normally. The remote mode is if the PLC is attached to a different PLC or to a computer that is and the computer is controlling the PLC. This is what we call a remote mode. The input-output section is the modules where we can connect the different inputs to the PLC and the outputs. This is an image of a real-life input or output module. We have different sensors or inputs that could be switches. This is a normally closed switch. This is a normal open switch. We have different other sensors that could be inputted to the PLC. So we have relay contacts, we have push buttons, we have analog sensors, we have digital sensors, of course, we have limit switches, we could have selector switches as well. So the term field and real world I use to distinguish actual external devices that exist and must be physically wired into the system, as well as we can have other inputs. So the inputs to the input module, this is a list of examples as well for the inputs to the input module. So a robot output can be sent to a PLC input where the robot has finished a program. So I can have a control that's not only from sensors, it could be from another machine, it could be from another PLC output that is inputted to the PLC. The output module. So the output module is connected to several real outputs like relays, motor starters, lab displays. We can have lamps, indicator lights. We can have anything that could be controlled, and we can also have values that are read back into the inputs or to inputs of another PLCs. A simple practical example in here of a one input, one output for a PLC is I have push buttons that are input to the PLC, and the output is a motor starter and it's starting a motor. So it depends on the program that I write. I could control the start, stop, for example, of the motor. We'll talk about the memory of the PLC. We can divide the memory into different parts. The ROM and the RAM, the read-only memory and the random access memory. In the random access memory, I can have some system-used memories, input, output status. I can have data, and these are eliminated when the PLC turns off unless I have a battery, a backup battery, so that if current runs out and back, especially in our country where we have current regularly running off, so that the machine doesn't start from zero state, continues from where it was. We need a battery backup for the values that are saved in the RAM. We have the memory, we have the boot, the one that allows the PLC to start, so this is in the ROM. We also have the program, which is saved in the EEPROM. The output section of the PLC provides the connection to the real-world devices, the one we just talked about. They can be purchased to handle DC or AC voltages, so I have different types. We can have TRIAC, we can have relay output, we can have transistor output. So the digital output just acts like a switch. It's either on or off. And the IEC 1131-3 programming, it's because it has been created because every company started to write its own PLC standards, and everyone was really different, so they agreed together to form a common basics, some common general rules. They're still not having the exact same way to program. Each company has its own software for its own PLCs. But, however, there is a standard that everyone is following. And the standard, it's like PLCs can be programmed in the most commonly used ladder logic because it looks a lot like the relay circuit that was before PLCs. It can be programmed by functional block diagrams, like these are a state diagram shape. We have instruction lists, C language, structured text. They are very similar, but they are all structured text, they are text. And you can see that PLCs are programmed in various ways, but the most common is ladder, and the second one mostly used is functional block diagrams. C language is sometimes used just when we want to do a program that runs really fast. A list of PLC applications would include process control, position and velocity control, cutting lumber, sizing them, food processing, electronic assembly, and many, many others. Some leading brands in PLCs, we have Rockwell, Allen Bradley, Gould Motican, Texas Instruments, General Electric, Siemens, Festo, Telemecanique, Toshiba, Omron, Mitsubishi, Delta. We have many others, but these are a list of the most commonly used PLCs. Most of them, we have them in Lebanon. This is the end of the first chapter. Thank you.